Right, hi everyone, and today we're going to be talking about this little circuit. Just bring it up, and it's a 1 watt cob light, and there it is, there's the little cob light. Got it upside down. And it's to be run off of 5 volts because I've got some main sockets that give me 5 volts. And so I wanted to work out the dropper resistors, what were needed for this. And there they are, 4 little dropper resistors. They're quarter watt resistors. And in the configuration I've got them in is series parallel. And what am I going to talk about that? Well, now at the moment we'll flip over to here, and there's our circuit, much better picture of it. And if you look very carefully, you can see it says 7R5. So there's 7.5 ohm resistors, 4 of them, 1, 2, 3 and 4. And all the resistors are there. And there is a circuit for it, and there's the circuit of what I've got. Now, why did I do it that way? Well, the reason I used 4 resistors is because I didn't have the resistor value I wanted in the right wattage. But using the 4 resistors in series parallel gave me the wattage I needed for the resistors. I needed a 1 watt resistor and I hadn't got one. I'd only got quarter watt resistors. That wattage adds to that wattage, that wattage adds to that wattage, that's half a watt, that's half a watt, all adds together to give me 1 watt of power that I can draw through there to run this 1 watt LED. Now, the maths for that will look, just centre me. Right, there's our circuit, and the mathematics for that circuit will be represented by that. Now, would you know how to do fractions? And the answer to that is not a lot of us know it. I can never remember how to do it, but we would have R1 plus R2 equals 15. We would then want the same for R3 and 4. So R3 plus R4 would 15, right? So there's 1 and 2, there's 3 and 4, add them together, 7.5 and 7.5 makes 15. Get your calculator out and do it if you want. Applications, accessories. There's a calculator, there you are, hiding there. Right, so we've got a calculator, and so 7.5 times 2, can't see my own keyboard, equals 15. Right, so now that proves that we got 15. Now there's 1 over. So what we have to do is we can add them together, which will give us 30. So 15 plus 15 equals 30. Fifteen plus 15 equals 30. I think you all agree with that. Now, but we don't need the 30. We can use the 30, but we have to go back. Let's calculate it on. So 15, where's the plus sign? Plus 15 equals 15 plus 15 equals 30. Okay, and now 30 divided by 2 equals 15, because we need to get to 15. 15 divided by 2 equals 7.5. There's the resistance I wanted, 7.5. So I've got my resistance. I know for a fact that at this point here, from there with respect to ground, is 3 volts. So from there to there must be 2 volts. So if I put my positive lead on there and my negative lead here, I should read 2 volts, because my LED is 1 watt and my LED requires 3 volts to make it work. So that means there must be 2 volts at this point. Can we prove that? I'll just finish this off. 30 divided by 2 equals 15. 15 divided by 2 equals 7.5. So that's where we want it to be. And we can only do that with this particular set of resistors because they are all the same value. If they were not the same value, we would have a lot more working out to do. And at that point, let's copy this, take it down here, start again. So we know that our value is 7.5 ohms. But because they're all the same value resistor, we're able to do the above equation to arrive at the point of that. Because this divides into this. No, this adds to this, and this adds to that, and the combined of that divides into that. And that's how it works. Confusing, I know, but you can only do it when all the resistors are the same value. So if you had 10 ohm resistors, you would have 10 ohms as your total resistance. So we got 7.5 now. Got 7.5 ohms. Now, we know the voltage is 5 and we know 7.5 ohms. And we know it's a 1 watt lead. So we can use the sum, we can use, oh, where am I going? Right, power. Need a bigger power and bold. Power equals watts. Power equals watts. And if we know it's 1 watt and we know it's 5 volts, we can do an equation, because power divided by voltage equals, do we all know what it's going to equal? Equals I, which is current, equals the current. So, back to our calculator. Let's clear the calculator. 1 divided by 5 volts equals 0.2. Okay, so 1 divided by 5 equals 0.2 amps. Okay, oh, maximum current that can flow is 1 divided by 5 equals 200 milliamps. The maximum current that can flow in this circuit at this point here is 200 milliamps. But this LED requires 3 volts so 1 divided by 3 equals 333 milliamps, but I'm only feeding it 200 milliamps, so I've not got the LED full on. I've not turned it full on, and the reason I've not turned it full on is because I don't want to run the LED flat out. That's bad practice. So I'm running it 130 milliamps less, and my LED will last a lot longer. So there you go. That's why I wanted that 0.75 ohms. And now if I use Ohm's law again, and 3 divided by 0.2 equals 15. So I wanted 15 ohms for the there, but I chose to halve 15. And what's half of 15? 7.5. Can you see the method in my madness now? I wanted to lower the wattage. Now, how many watts is this going to handle? Well, I know it's going to be up to 1 watt, but how many watts at this do I need to have the resistors? That's my next question. And we know from Ohm's law, if we want to know the wattage of something, it's the volts times the amps. So 5 times 0.2 equals 1. 5 times 0.2 equals 1 watt. 1 watt of light. So we've proved we were getting 1 watt from our 200 milliamps. So 3 times 0.2 equals 0.6 ATT. Resistor. So that means the resistor's got to be at least 0.6 of a watt. At this point we've got 200 milliamps flowing across the diode, the LED, and we've just proved that this resistor needs to be 0.6 of a watt. Well, we know combined it all comes to 1 watt, so we've got more than enough. So 5 times 0.2 equals 1. And we've got a 1 watt LED, and we've got 200 milliamps. What's 5 divided by 0.2? It's 25. Let's do it with the resistors. So 5 divided by 7.5 equals 666,666. So the maximum current that can flow there is 600 milliamps. But 3 divided by 7.5 is 400 milliamps. Oh, I know what I've done. It's not that 3 volts, it's not that. What voltage have we got across here? From there to there, what voltage have we got? If we've got 3 from there to there, we've got 3. 3 from 5 leaves 2. And I've been using the wrong voltage. Who's a silly Billy? So 2 divided by 0.2 is the voltage we're looking at, equals, let's go to the calculator, 2 divided by 0.2 equals 10 ohms. So 2 divided by 7.5. 2 volts divided by 7.5 equals, and that will give us our amps. Two divided by 7.5, 266,666,667, so 0.267 amps. 266 amps. That's the maximum that can flow. At 2 volts, the maximum amperage can be flowing at 2 volts is 0.2667 amps, which is just over 250 milliamps. Well, we know we was looking for 200 milliamps, and we're very, very close for 5 times equals 1 watt. 5 at 200 milliamps is 10 ohms. We used 7.5, so 2 divided by 7.5 means the maximum current that can be flowing in that circuit is 266.7 amps. Milliamps, sorry. 0.266.7 milliamps. That's the maximum. Now we can convert that to watts. How do we change that to watts? 2 times 0.667 equals, let's go and have a look. 2 times 0.667 equals 1.34. Is that right? 2 divided by 7.5 equals 266. Oh, 2666. 7, right. Times that by 2 equals 500, times that by 2, which is the 2 volts again, times it by 2. 2 volts times, doesn't matter which way round you do it, you have 533 watt milliwatts, 530. Oh, you rat bag, undo that. Where's undo? Copy, cheat, and paste. So we proved that that little circuit works because we're measuring the voltage that's across it and the wattage across it, maximum wattage flowing, is 533. Hence I needed more than half a watt, and with 4 resistors I ended up with a 1 watt. So I doubled what I needed, and that's how we worked out our circuit. And then we made it, and that's it. For this to work. There you go. That's proved my resistor wattage theory works. Because across here, between here and here, we've got 2 volts, and between here and ground we have 3 volts. Across here and here we'll have 5 volts if we measure it. If we measure from here and move the ground to here, we'll have 2 volts. If we measure the positive on here and put the ground on the ground, we'll see we've got 3 volts. Oh, sorry. We'll see we got 3 volts. Oh, go away. We'll see we got 3 volts. So measuring from here to here, we'll see we got 3 volts. Positive, negative, and we'll have 3 volts. Cut. Well, I hope you like that one. Don't forget, if you're watching on YouTube, give it a thumbs up. If not, if you're watching on Library, leave me a tip. That'd be nice. And the next one, I'm going to make a dimmer control for this. I want to make a 5 volt dimmer control. That's the next little trick. So, hope you enjoyed it. Catch you all again. Don't forget, john.lovatt.524 on Facebook. Is it at the bottom of this one? Can't remember if it's at the bottom of this one. No, it's not. Oh well. Not on the bottom of that one. I just went and had a look down, scrolled down, and just having a look at my messy old workbench, and that's what we got. So, catch you all later.